Welcome, everybody. We're going to get started here now, 9:45. Today, we've got kind of a session split in two for you all. We're going to start with an overview of the NVMe Transport specifications, and then we're going to go into some time on the NVMe command set specs. So with that, we're going to get started. Our speakers today for the transport specification overviews, we've got John Geldman. He's going to come up and share with us a little bit of background as well as the PCIe transport spec. Curtis Ballard, who's a distinguished technologist at HPE, is going to be the person that we've got sharing about RDMA today. And then Sagi Grimberg, who is the CTO at Lighbits, he is going to share with us about PCIe transport spec for NVMe. So our agenda today, first thing we're going to start off with is a bit of an overview of the refactoring of 2.0 and specifically how that impacts the transport specs and the command set specs. Then we've got some time for PCIe, RDMA, and TCP. That'll be followed by an overview of the command set specifications. ZNS, the zoned namespaces command set, as well as KV, the key value command set spec. So with that, we are going to get started, and I'm going to introduce John Geldman.
Thank you. So I wanted to talk a bit about refactoring first, because it largely had the biggest effect on the PCIe transport part of the NVMe over PCIe transport specification. When we started with NVMe Express 1.0, we had a register level interface for host software to communicate with a non-volatile memory over PCI Express. It was all integrated in one document, and we really squeezed PCIe in on it. One of the things that happened at 1.21 is we introduced the first fabric spec. And that was a big change for us. And we started the separation a little bit of fabrics. Well, by definition, we had the fabrics in PCI, but PCIe was still based into the base spec. The fabrics included several interfaces. We had Ethernet, a couple of ways in InfiniBand, which we did through the TCP and RDMA, and then Fiber Channel did their own spec. And at the time, some of the support requirements for feature and functionality, well, they differ. So PCI Express was the original NVMe transport. We had PCI Express as the backbone. The two specs have an awful lot in common in terms of their scalability, their latencies. It is still probably the most popular NVMe transport. It is certainly the most common. It's in all of our laptops and desktops and many other places. And both as NVMe was being developed for efficiency and latency, PCIe was the natural partner. We introduced uses of that with multiple command and submission queues, doorbells, MSI. Those were all PCIe features that we took very good advantage of. That efficiency is the focus of both. So now, after the refactoring, NVMe Express is relatively independent of PCI Express versions, and that's been really good for us. And we've been working on removing some of in the early specs, we tied the spec very closely to PCI Express 3.0. We've been removing those couple of requirements, and I think we're pretty good now. And now we get to ride the performance increases that are coming from PCI Express. In our environment, in the NVMe environment, you'll see two different places where the PCI Express interface has requirements. One of them is the NVMe over PCIe specification. That's something which was created during the refactoring. And that took most of the PCIe stuff as much as we could do and put it in its own world and gave it its own context. And then the NVMe management interface also has some PCIe requirements. And that enables things like a VDM for management across the PCIe bus. So one of the things we've been able to do is ride the performance ramp. And that's been an awful lot of fun. And you've probably seen in simply available devices the increasing performance from PCIe 3.0, which was, let's see, I don't want to turn the pointer on, which was basically at 8 gigabits per lane to PCIe 4, which is now 16 gigabits per lane. And that whole generation of devices has been pretty good for the market, that increase. And the one which is coming out now are ones based on Gen 5 or 32. There's also another one which has been released by PCI SIG, which is their Rev 6, which actually changes from NRZ to PAM4 encoding, which gets you up to 64 gigabits per lane. So with many of our 4-lane devices, it's really astounding throughput if you've got the power for it. PCIe has announced in several places, press releases, that they're now working on 128. That's going to bump the frequency to 64 gig and continue to use PAM4. The other thing that we've gotten to do with make use of PCI Express improvements is feature improvements. So there are some features coming that aren't common in NVMe SSDs today. We're not really requiring them in NVMe Express. They will be product implementations using the PCI Express. You've got content measurement and authentication. That basically allows the host to authenticate that the device is what it says it is, to review and measure the firmware in the device to make sure it hasn't been tampered with before it brings it up in the system. There is an IDE, or integrity and data encryption, which basically allows PCI SIG level across the wire encryption. That can be point to point, or it can be all the way through the system, all the way from the root port to from the source point all the way through the destination point through a PCIe fabric. And they've also been doing some fun stuff in combined power. And I may be a bit of a power wonk, but I find that stuff interesting. It basically introduces a whole new power budgeting capability for systems where the current slot power is a little bit hard to work with. PCI 6 introduced a couple of new features. One of them is FLITs, flow control units. This is a complete restructuring of what a PCIe packet looks like. Instead of being a TLP or a DLP, you now have a structure which carries TLPs and DLPs. And it turns out that that whole backbone is a lot more efficient, and it comes with fun stuff like forward error correction, which is particularly useful when you get to the signal integrity worries of PAM4. Another fun feature, which is, again, transparent to the NVMe world, but is a great PCIe feature, is the L0P. And that's going to allow us on our multi-lane devices to basically have a gear shift without a stall that lets you go from 4 lanes when you need all that power down to 1 lane when you don't, and back and forth as many times as you want. And all of that without a stall. That capability existed before, but it cost you a stall. Okay, and I think that, one more. So we're riding the feature improvements, and I think we're working well together as organizations. Personally, I'm currently a temporary chair in PCI SIG for someone who's out on sabbatical. And of course, I am on the board of NVMe, and we work well together. There's many of us who are active in both organizations. So there are some ongoing activities there, and to really get more information than this blurb, you really need to go to PCI SIG because we can't talk about that stuff outside of it. But there is a trusted execution environment, and that's basically setting up ways for hosts to be able to set up a trusted module and then freeze that trusted module and then give the keys to the module so that no user information is accessible from that module until it's set up. And once it's set up, it can be used until it's torn down. And the other fun thing that's coming is a standard way to do I3C basic, which will improve one of our main sideband buses. Key things that we want to avoid doing is have across the PCIe infrastructure or ecosystem, we want to have the same voltage and the same way to go from SM bus to I3C and back again as appropriate. And now I think I'm done. Curtis? Actually, you should probably be introduced. You go for it, Curtis. All right.
Thank you, John. Curtis Ballard, a distinguished technologist with Hewlett-Packard Enterprise, on the NVM Express board of directors and active in a number of other industry committees. They've asked me today to talk a little bit about the NVM Express RDMA Transport specification and how the refactoring, the changes we made in 2.0 would help the industry. When I was asked to talk about this, I thought, wow, what can I talk about for the RDMA transport specification? It just works, and it's a really simple direct mapping to the PCIe interface. So it seemed like there's really not a lot to talk about. But then if you look into what's behind the RDMA interface, it's not really super simple. There's a lot of complexity in the background, but one of the things that the NVM Express organization did, and the people on the technical work group, as they were developing the NVMe Over Fabrics architecture and specifications, they carefully layered their architectures and built on top of what came before. So a lot of the things that are some complexities about transports disappear into transport generic functions that work the same across all of them. So John touched on a little bit in his slides, and I don't have a slide to it here, but the core architecture for NVMe Over Fabrics was designed separate from the specific transports that would go underneath it. So part of what we accomplished in the 2.0 refactoring was we were able to take that core transport architecture for NVMe Over Fabrics and move it into the base spec, closely integrated with all the other pieces of the base spec, and it's just a core part of NVM Express and NVM Express Over Fabrics. And for RDMA in particular, there's a whole RDMA specification that was developed originally by the InfiniBand Association, and there's all sorts of complexities there, but it's at a layer below where we need to do NVM Express mapping. So the NVM Express mapping actually turns out to be incredibly simple, and what was accomplished in the 2.0 refactoring was revealing how nicely, cleanly, and how simple mapping is for NVMe Over Fabrics onto RDMA. I've worked on other transport mapping specifications. This one is 16 pages of, I call it, of simplicity. Compared to the other transport specifications I've worked on, I don't think we got through the index in 16 pages. So a lot of this is document structure, and it doesn't take a tremendous amount of content to map the RDMA operations onto the core operations that were part of the original design because of the PCIe implementation. So that was really revealed by pulling it into its own specification. So what went into the 1.0a specification that makes it different from what was in the 1.1a specification? Well, if you're a implementer that's implemented to 1.0a, you can rest easy that the 1.1a specification and the new RDMA Transport specification 1.0a that's part of the 2.0 bundle of specifications are functionally equivalent. So you don't have to go do a bunch of code changes to update to the 2.0 specification bundle. And that's one of the things we're trying to show with the 2.0 bundle is the transport specifications can remain relatively unchanged as features get added into NVM Express. So what did we do in 2.0 that changed the RDMA specification? Well, we tried to make it easier to implement. We learned a little bit from people that were implementing to the original specification, and it wasn't aligned as cleanly with RDMA technology terms and RDMA specifications as we would like. So basically we did a bunch of cleanup. The changes that went in include incorporating some definitions from the InfiniBand specification for generic RDMA terms. You match your terminology and it's easier to all speak the same language. We aligned the definitions, we aligned the terms, and then we put together a bunch of document structure and introductory text to make it be available its own separate document. And that's it. The 1.0a specification cleans it up, makes it a little easier to align with the rest of the industry, and pulls it out into its own simple specification, ready for everybody to use and implement. With that, I'll hand it over to Sagi to tell us about what's up with TCP.
Hello. Okay, so if you're not familiar with NVMe over TCP, the NVMe over TCP is the transport binding spec for NVMe on top of standard TCP/IP. The current version of the spec is 1.0b, and it's 35 pages long. Also not that big. And I guess it wouldn't be shocking to see what it defines, which includes setup, initialization, what's the queuing model, or how you map NVMe queues to TCP streams. The data transfer model, where that is traditionally been defined in different transports like RDMA or fiber channel. With TCP, it's really stream based. So the messaging protocol is defined in the spec itself, or the transport binding spec itself. The wire format, error handling, and also data integrity, header and data digests, and security related items for in-transit encryption or TLS. And if you haven't read it, it's very recommended. I'm kidding. All right. So in terms of what are the updates? There was an update for TLS 1.3 option, which is highly encouraged, given that the first revision of the specification 1.2 was state of the art. So 1.3 has a new security type in the discovery log page header. To make sure that the host understands the controller supports TLS 1.3. And another one was enhancements on in-band authentication. But what's more important is the way that you can, or I would say, concatenate TLS session establishment on top of in-band authentication. So you don't need to manage two sets of keys, right? TLS and NVMe over TCP is defined with pre-shared keys, meaning that you need both the host and the controller be aware of the keys that are used to authenticate. The same thing is defined in NVMe in-band authentication, so you don't need to separately manage two sets of keys. You can actually use authentication to what's known as generate a pre-shared key on top of the authentication transaction, and then use that to establish a TLS session. So that's a nice addition. Other related sort of work in progress technical proposals. So we have authentication verification entity. That is basically defines how you interact with an entity that can offload as a controller. If you are implementing an NVMe controller and want to support in-band authentication, you can, just like if you were to offload that to an LDAP server or an Active Directory for stuff like control planes. So in-band authentication, you can offload that to specifically an authentication verification entity. That's still something that's a work in progress. People are interested in that. And the second one are using certificates for TLS authentication or TLS setup, which is a nice improvement and could pretty much eliminate the use of key certificates. Are sort of well-known practice on how to manage, how to rotate them. But that's another sort of technical proposal that's a work in progress. I think Costa is leading that one. Another related, already ratified, that are maybe indirectly connected to NVMe over TCP is the what's known as automated discovery on top of IP fabrics of the discovery service, which is a weird name, but the discovery controller is something that's well known in NVMe. Tells you where your I/O controllers are in the fabric. There's a problem that you don't have a way to discover the discovery controller, so there's a way, new specification or new TP that defines how to use DNS service discovery to discover the NVMe discovery controller, or controllers, plural. And that is something that's already been ratified, and I know that people have been implementing that as well. The second one is the centralized discovery controller, what's known as the CDC. And the only connection it has to NVMe over TCP is that it only runs, or it's only defined on NVMe over TCP. It's a choice that was taken maybe for simplicity, but I think it was thought and designed in mind with an NVMe over TCP fabric. And the third one is the boot specification. That's also, I think, the first revision is also targeting primarily NVMe over TCP. So these are sort of related directly or indirectly to NVMe over TCP, but some efforts that are done in the specification space. A bit about the ecosystem. Linux was the first one to get support for NVMe over TCP, similar to the other NVMe transports. But support is maturing. There are more bug reports, more testers, and more devices that we're seeing in the wild. So it's either the most broken transports or the most tested transports, but all of the bug reports, or most of them outside of PCIe, comes for TCP. Toolchain and user space tools are expanding to natively support NVMe over TCP, or actually target NVMe over TCP. It relates to the other specifications or technical proposals that I mentioned. In-band authentication is no longer pending inclusion. It has been included, which is very, very, I view it as a very big step for Linux, and we encourage other operating system vendors to do so. And also TLS is something that's in the works. There's a working POC from Hannes. Is Hannes here, by the way? No. Hannes implemented the first POC of NVMe over TCP on top of TLS. Turns out that this is a joint work with the NFS people, because NFS also want to run on top of TLS, so there's an attempt to find sort of a shared mechanism to use both NFS and NVMe over TCP on top of TLS. I won't get into the weeds of that. What else is new is that it's now supported. NVMe over TCP is now supported in VMware, included in 7.0U3, which is good. 7.0U3 has been updated a number of times, including fixes to NVMe over TCP and NVMe in general. There are zero-day partners, specifically 2 of them, that has contributed to make that sort of production ready, and it's already running in production. We're seeing that, and that's a very big improvement for the ecosystem. And the last remaining prevalent operating system that still does not support is Microsoft. Do we have any Microsoft people here? No, maybe. But there are some Windows drivers out of non-inbox that are in the wild, but we're hoping to see it inbox in Windows as well.